Hi, I'm Dulcinea Carroll, and I'm going to be discussing human motion analysis technology and its advances over the years, as well as its applications and uses. On the right, you can see some of the many companies that currently use this technology. Their products range from movies and video games to robotics and programs on smartphones. Here are some examples of how motion capture and analysis is used in the real world. It can be used in the sports field to track progress and help prevent and diagnose injury. It is also used in television, film, video games, and other animation to help create characters and modify their appearance, like with Mark Ruffalo as the Hulk and Tom Hanks in The Polar Express. The first instance of motion capture technology was the rotoscope in 1915. Rotoscoping involved filming an actor and then projecting that performance onto a transparent surface and tracing the movements frame by frame. This creates lifelike motion like what is seen in Snow White and the Seven Dwarfs. The Animac, made in the 1960s, was the precursor to the bodysuits with the white markers that you may be more familiar with. The Animac involves analog circuits and cathode tubes. It recorded and animated motion in real time. After the Animac, the early days of mocap involved assigning markers to parts of the body and hand digitizing the movements frame by frame. When processing speeds improved in the 90s, it allowed for serious progress in mocap technology. Now you don't have to work frame by frame. Motion capture is automated and trackable in real time. It has gotten much faster and easier to use, allowing for more time to be put towards other aspects of production. Lots of uses of mocap don't even need markers anymore. This can be seen on some smartphones with facial motion capture, on AR Emoji and Animoji, as well as other apps. With such easy access to mocap technology, it has expanded to many different fields. 50% is used in biomechanics, like gait analysis and treating patients, a quarter in video games and film, and a quarter in robotics, like VR and autonomous driving. Motion capture technology is now a very valuable technology. You probably have had the most exposure to it in entertainment. Earlier creations that used rotoscoping were Snow White and the Seven Dwarfs, Alice in Wonderland, and Cinderella. Some films with more modern mocap used are Ready Player One, Titanic, Paddington, the Marvel Avenger universe, and many Star Wars films like The Last Jedi. It has also been used in games like Hellblade: Senua's Sacrifice, Life is Strange, and Fortnite. Another field where motion capture technology is beneficial is in sports medicine. By observing athletes doing tasks and movements that are likely to cause acute or long-term injuries, we can identify ways to improve performance to address and prevent the injury. We want to use this technology to minimize the amount of sports injuries that take place on the field. It can also be used on the flip side to assist in physical therapy when an athlete is already injured. In addition to helping athletes, this technology can be used to help people with mobility impairment. Some debilitating conditions it has been used with are Parkinson's disease, Huntington's disease, CP, and MS. Researchers used mocap to figure out how these diseases affect the patient's walking and mobility, and possible ways to assist them and improve mobility. It has also been used in a similar way to help the elderly with increasing movement and limiting falling. Another application of motion capture technology is with ergonomics and product design. Ergonomics is when human interactions with elements of a system are used to design and optimize usage and system performance. Human motion capture can be helpful in tracking the human interaction with the system being designed or improved. When gathering data for ergonomic designs, you take into consideration position, complexity of movement, and obstacles in the workplace. Mocap in ergonomics, like in sports and entertainment, has become more accessible and easier to use, causing it to be more commonly used. Advances in the technology have allowed individual athletes, sports teams, and physicians to monitor functional movements, workloads, and biometric markers to maximize performance and minimize injury. The smartwatches you may be familiar with have similar motion analysis components with movement sensors like a pedometer and physiological sensors like a heart rate monitor. Thank you for listening, and to learn more, visit www.wrslab.com. Below are my colleagues and my email if you have any questions or would like to reach out to us. Thank you.
Hi, my name is Luke Majette, and today we'll be going over the fundamentals between different types of motion capture, as well as comparing the pros and cons of each type. On the most basic level, human motion analysis is the study of the body structure and the science behind observing the body as it moves and performs various tasks. Be it running, dancing, skating, or any other activity, observing the body in motion can produce valuable data about human abilities and human weaknesses, and can be used for other purposes like entertainment. When watching a body undergo motion, it is usually tracked from one or more angles, and oftentimes a model is made of that motion to describe and quantify the motion being observed. One of the subsets of motion analysis is gait analysis, where a patient walks and the quality of that walk is determined via analysis. This is based on the gait cycle, which is made up of steps and strides. A step starts with the initial contact of one foot when a heel hits the ground and ends with the initial contact of the other foot. So from when the left heel hits the ground to when the right heel hits the ground, or vice versa. Strides, on the other hand, start with the initial contact of one foot and ends with the initial contact of that same foot. So think a left foot and then a right foot, and then when the left foot hits again. And when measuring a patient through gait analysis, be sure to consider the individual factors such as the terrain. Obviously, a patient walking on rocky substance is going to be different than walking on flat land, and make sure to account for their gender and age and their height and weight when considering how they will walk. Also, be sure to measure different parameters such as their step and stride length, as well as the speed that the patient can walk at and their foot and hip angle. Now, the first type of motion capture that we'll talk about today is called optical motion capture. To gather data about human motion by this method, a large system is needed with a lot of pieces, but the system can produce very detailed and valuable data. Infrared cameras track the distance between the camera and markers on the patient, which are placed at key points of bodily motion, like the joint shown on the skeleton. And on that skeleton, when clusters of markers can be placed together, as denoted by these little red diamonds, you can see these individual segments of the body can be studied individually, and then you can also measure how the segments move relative to each other. So how one leg moves and how that one leg moves relative to the other leg, for example. And back to these IR cameras, at least more than one camera is used, usually two on two separate walls in a room, with 2 points of XY data for the same one marker on the body. A 3D coordinate can be made to determine where that marker is in space. With a lot of these markers, the image of a person is moving is formed by the data, which can then be processed by computer software for analysis, either for animation in entertainment or diagnosis in clinical or athletic settings. For clinical settings, a treadmill can also be used to get a long recording of a patient walking at a continuous rate, which can be kept and recorded for later use or varied to test different speeds, and it keeps the patient in place if you're working in a small environment. Some of these research labs treadmills also have force platforms in them, which are shown by this video to the left. Now, these force platforms, they can determine the amount of weight and pressure being put on a certain part to determine how the body is balancing itself. And these treadmills can get a lot of data, steady data in a small location. And while this is nice, because treadmills are set at a certain speed, the patient loses control over how quickly they want to walk. To further reinforce this idea of two XY planes making a 3D space, here are some examples of a body being tracked through joint markers as it performs different actions. My favorite one is the jump, where you can see each of the little joints as they would have made the jumping motion with the body. Now, the next type of motion capture that we'll talk about is inertial measurement units, or IMUs, which are made up of microelectrical mechanical sensors, or MEMS. These often consist of a 3-degree freedom accelerometer, a gyroscope, and a magnetometer. These come in small form factors and can often be attached to various parts of the body, like the markers from optical motion capture, and they have become very popular because they are compact, affordable, and widely available in the market. The first sensor, the accelerometer, is an electromechanical device that can sense static or dynamic forces, such as gravity, vibrations, and movement. Similar to the idea of a mass hanging by a spring, the amount that that spring moves can be measured and analyzed as the mass undergoes a force. The next sensor is the gyroscope, which measures the angular rate by means of the Coriolis force. Like the idea of a mass within the sensor is undergoing a velocity, and when a rotation is applied to the mass, the Coriolis force is experienced, and this force can be quantified and measured to determine rotation. The last sensor, the magnetometer, can measure the Earth's magnetic field, which is used to determine the orientation of the IMU relative to the North and South poles. When a magnetic field affects a current, the charges will be attracted to one side of a metallic sheet, like pictured in the images on the right, which can be measured similar to the idea of a compass. Now, the last type of motion capture we'll talk about is computer vision motion capture, which is much more reliant on computers and benefits from not having any attachable parts to the patient, usually relying on an array of sensors like an IR blaster to track a motion. Both of these Microsoft products are used for different types of motion capture, the Azure for health and technological development, and the Kinect for real-time motion-tracked gameplay. Now, with each of these types of motion capture systems, and as well as the quality of the data that you want to get, there are different price points. For consumers, like low-end stuff like you and me, we'd be buying something along the lines of those Microsoft Kinects, which can run plus or minus $300. For low-scale market uses like low-budget movies or not high-quality data analysis for personal use, an IMU suit would cost between $500 and $10,000, and camera-based, more optical systems would cost between $2,000 and $15,000. And on the other hand, for research, non-market uses where you are trying to get as detailed data as possible, they can run between $50,000 and $100,000. And in summary, to compare and contrast the three big types of motion capture, optical motion capture, while it is more expensive and physically restrictive, the data that you get is much more accurate and increased visibility. The idea is that you have to have an entire dedicated room just to motion capture with all the cameras and the setup. IMUs, on the other hand, are much more affordable and they're much more portable, but the data is slightly less accurate for extended periods of times, and you don't get absolute positioning relative to the environment. These IMUs are just a suit, so they can be taken anywhere, which kind of opens the door, especially for entertainment. Now, computer vision comes at a low cost and is easy to set up. There's no calibration and there's no attachable parts to the patient. But the trade-off here is lower accuracy, and they're environmentally restrictive and light sensitive. Like this GIF here, this is kind of within perfect conditions, and you can still kind of see the thumb glitching in and out, which is kind of a shame. Well, that's the end of our presentation. We'd like to thank you for watching, and my colleagues' emails are here if you have any questions for a later date, but we'll take any questions right now. Thank you. Hi. In this presentation, we'll be going over the different classifications and applications of robotic exoskeletons, a subclass of wearable robotics. My name is Luke Majette, and with my colleague Dulcinea Carroll, we look forward to teaching you today. Wearable robots are a subclass of the large field known as robotics. Robotics encompasses everything you think about with robots, from shipping drones to military advancements, or this Atlas robot pictured here. Within that large field, wearable robotics deals specifically with robots that are made to be contoured by the human body and operate with them, like this Honda walking assistance device for mobility and comfort. Within wearable robotics, the further classes are robotic exoskeletons and prosthetic robots. Robotic exoskeletons cover and add to an existing part of the body, usually to strengthen an injured limb or expand human capacity. Prosthetics, on the other hand, aim to replace a limb that is missing entirely. An important definition is that robotic exoskeletons are active mechanical devices that are essentially anthropomorphic in nature. They are worn by an operator and fit closely to his or her body and work in concert with the operator's movements.
What is the purpose of wearable robots? Why do we use them? Wearable robotics nowadays are used in many fields, from in factories to hospitals to even in the home. They have been used to improve worker safety with injury prevention and increase worker productivity and endurance. Medically, they can be used to help in physical therapy with rehabilitation and increased movement for people with mobility impairments or paralysis. In the photos, we can see some examples from the medical, military, and industrial fields. Exoskeletons and wearable technology began with mainly medical purposes, both training and assistive. They then expanded more into military usage and then industrial and commercial, making this technology even more accessible. Exoskeletons versus prosthesis. Both are examples of wearable technology. They have key differences in form and function. The exoskeleton has two main purposes: empowering and orthotic. Empowering exoskeletons are used to increase the user's strength and endurance. They are modeled on the wearer's body. It has been used in the military to allow soldiers to travel long distances while carrying gear. They take the weight from the pack and redistribute the pressure to the ground or a lower impact part of the body. Empowering exoskeletons extend stamina and reduce fatigue for the user. Meanwhile, the orthotic exoskeletons are designed to assist in motion as a mobility aid or restrict motion as a form of physical therapy and rehab to train the wearer. This is modeled after the wearer's limb or body part. Orthotic exoskeletons can be used to assist the elderly or those suffering from a stroke or spinal cord injury in increasing movement. Prosthesis, rather than assist a body part, is designed to replace a body part. Prosthetics are helpful for people who have lost a limb. People can be born with limb loss, have a limb amputated, or have a severe injury to a limb. When you think of exoskeletons, you may think of a superhero you know and love, Iron Man. A more realistic example is the Raytheon XOS-2 exoskeleton. It has been called the real Iron Man suit because of how it can enhance the wearer's strength and endurance, reminiscent of Tony Stark's suit.
Now that we have a general grasp of what exoskeletons and prosthetics are, we'll go over the different classes of exoskeletons. There are many types of categories each exoskeleton can fall into, and these distinguishing features can help determine which exoskeletons serve which purposes. One of the most important classifications for exoskeletons is their application, or more broadly, the field that an exoskeleton is used in. Military exoskeletons are used to augment human ability and empower soldiers. Like in the Bleaks shown here, the robotic muscles work in parallel with the human muscle, allowing the soldier to carry a very heavy load without fatigue. Industrial exoskeletons assist workers with bodily fatigue, and similar to military applications, can be used to augment human abilities to exceed natural limits. Consumer exoskeletons serve to improve human ability for sport and prevent injuries by supporting the human body during athletic endeavors. Medical exoskeletons can also be used for two large groups of applications, explicitly defined as training devices and mobility aid devices. Mobility aids assist patients who will never be able to achieve normal motor ability, and these suits serve to replicate human ability and assist these patients with independence. The common analogy for these devices is that a regular human muscle is a bike. These mobility aids are an electric bike, adding a motor to the existing ability to improve function. Trainer devices, on the other hand, rehabilitate patients who have experienced injury, such as a stroke or spinal cord injury, and assist those who have struggled with motor function. These devices are used by physical therapists and are permanent fixtures in hospitals, working with patients toward a goal of them no longer needing the assistance that this device provides. To return to the bike analogy, these trainer devices are likened to training wheels, which are temporarily added to a bike until the rider no longer needs them to ride. The next classification for exoskeletons is that by body segment. Lower body exoskeletons operate between the hip and the foot, spanning the other joints in between as well. Upper body exoskeletons operate between the neck and hip, also including the back and joints in the arms. Full body exoskeletons can come in many varieties, being active in a combination of any of these joints. An important concept when discussing exoskeletons, and particularly the classification of exoskeletons, is degrees of freedom, particularly those in your joints. The degrees of freedom of a joint is the minimum number of independent parameters needed to define a joint. When dealing with exoskeletons, relative degrees of freedom are the metric being measured, and they're often a metric for how complex a system is. The human body has different types of joints, just like exoskeletons, which can be classified by the degrees of freedom each has. Some of your joints only allow for one degree of freedom, such as your knee, which only moves about a single axis, known as flexion or extension. An example of a joint with 2 degrees of freedom is your elbow, which can be flexed but also can be twisted. Finally, a 3-degree of freedom joint would be the shoulder, which acts as a ball joint relative to the torso. It can flex and rotate in 2 different axes. Now that we know what degrees of freedom are, we can recontextualize them in the scope of exoskeletons. Like the joints on your body, different exoskeletons can be classified by the degrees of freedom each has. The example here with 1 degree of freedom is a project from the Stevens Wearable Robotic Systems Lab, which has its 1 degree of freedom at the joint between the foot and the ankle. The example with 2 degrees of freedom has those 2 degrees of freedom moving in the elbow, moving it straight and curved, and also twisting the forearm, just like the joint on your body. The 3 degree of freedom example has its 3 body segments at the hip, the knee, and the ankle.
Another classification is by whether an exoskeleton is a monoarticular or biarticular mechanism. Monoarticular means that there is one motor per joint, while biarticular means that the motor spans multiple joints. The monoarticular example is the exoboot. The exoboot only addresses one joint, the ankle. On the right is Harvard's soft exosuit. This suit has straps that reach from the hip to the ankle joint. It works with hip flexion and ankle plantar flexion. The load path passes directly through the knee joint, so there is no net torque exerted on the knee joint.
Another classification is by portability, which is broken into two main sections, fixed and portable. Fixed denotes an exoskeleton that is permanent and immobile, like that pictured at the bottom left. These structures are often used to rehabilitate patients after suffering a spinal cord injury or a stroke. Portable exoskeletons attach to the patient's body and keep attached to the patient as they go about their day, and are used for a wider variety of applications. The next classification for robotic exoskeletons is that by anchoring point, or the type of force exerted by the device. Internal force exoskeletons have anchoring points on the wearer's body and distribute forces across the body, as exampled by the Darwin product below. The force on his lower back is redirected by the exoskeleton to ease back pain and improve endurance and weight capacity. In external force exoskeletons, the anchoring points are off of the wearer's body, often on a wall or ceiling mount. These devices redistribute the wearer's forces to the ground, like the Lacomat shown below. The patient's forces are grounded by the exoskeleton. Another classification for exoskeletons is their rigidity, which is broken into two categories. Soft exosuits, as the name implies, don't have any hard structure and are usually very close fit to the body of the wearer, like the Harvard shoulder exosuit pictured on the left. The device uses a fabric to attach to the body in a form-fitting fashion. Rigid exoskeletons, however, use hard mechanical structures to serve their intended purpose. As shown by the metal structures on the obliques, without these rigid structures, the device wouldn't be able to transfer heavy forces down the body.
Passive versus active joints. There are three variations in exoskeletons. The main difference is the usage of motors. Passive exoskeletons have no motors. They are mostly used for gravity counterbalance. These exoskeletons can be useful as support to prevent injuries from repetitive tasks or as help to hold tools. The image below shows an exoskeleton for workers that need to hold things like a drill up high for extended periods of time. The device redistributes the weight of the tool and the wearer's arms to a lower impact point of the body, the hips. Active exoskeletons have joints controlled by motors. Though not every joint needs to be active to make an exoskeleton active. There can be a combination of passive and active elements. One of the many ways active exoskeletons are helpful is with lifting heavy objects and preventing injury. Semi-active exoskeletons have the primary action as passive, but use a motor and an elastic element, like a spring, to adjust the structure for the wearer. It can adjust the assistive or restrictive level, which can be helpful for rehabilitation uses. Thank you for listening. To hear about examples of exoskeletons and their classifications, watch part 2 of Powered Exoskeletons for Assistance and Rehabilitation. Hello, this is part 2 of Powered Exoskeletons for Assistance and Rehabilitation. My name is Dulcinea Carroll, and my colleague is Luke Medjett. And in this presentation, we will be going over some examples of exoskeletons and what classifications from part 1 they fall under. We are going to discuss application, body segments, portability, anchoring points, and passive versus active joints. When you see the devices, pause the video and try to guess which classifications they fall under. Our first example is the carry suit. The carry suit is used to help carry heavy things. The function is useful in the work world, so the application it falls under is industrial. To help with these heavy loads, it reduces pressure on the hands, arms, shoulders, and back. As these body parts suggest, it is an upper body focused exoskeleton. It is portable because it can be brought to wherever it is needed. The anchoring points of the exoskeleton are on the wearer's body, so it's classified by an internal force. The last classification we're going to discuss is whether it is passive, active, or semi-active. The suit is passive because it uses no motors in its function. Now we are looking at the exoboot. The exoboot is an ankle-only exoskeleton. It is used to assist in walking and increase endurance while decreasing energy expenditure. The application of the DeFi exoboot is for military usage. And as it is ankle only, the body segment classification is lower body, more specifically, lower leg. This is a portable device with no fixed location. The anchoring point is on the wearer's body, so it is classified by an internal force. Lastly, this device is active because its function is motor-based. Here is the Exomotus. The Exomotus is an exoskeleton to help with safe walking and retraining. For these reasons, the Exomotus has medical applications. In the medical field, it falls under both a mobility aid and a rehabilitation device. As its focus is walking, it is a lower body device. It has no fixed location, so we can safely classify this as a portable device. Unlike the majority of portable devices, this exoskeleton is classified by an external force due to the foot plates that directly transfer the weight to the ground. It is also an active device because of the major use of motors to power the joints. This is the Walkbot. It is a gait rehabilitation exoskeleton. Because of this, it is for medical uses, specifically as training or rehabilitation. The body segment it focuses on is the lower body. As you could probably tell from the photograph, this exoskeleton has a fixed frame. And as with most fixed exoskeletons, it has an external anchoring point. It is also classified as an active device because of the motor-controlled joints. The last example we will be examining is the Ski Mojo. The Ski Mojo is a shock-absorbing device used for skiing. It relieves pressure from the knees. This exoskeleton, unlike the others we looked at, is a consumer-level device. It is used to relieve pressure from the knees while skiing, so this is a lower body specific item. It is portable with no fixed frame and has anchoring points on the wearer. This means that it is controlled by internal forces. The device has passive joints because it has no motors and uses a spring dampening system to absorb the pressure on the knees. Thank you for listening. To learn more, visit www.wrslab.com. If you have any questions, feel free to email me or my colleague with our emails below. Thank you.